Hello बच्चों, कैसे हो सब? Welcome. So today we're going to dive into Unit 8, Electromagnetic Waves. I know, sometimes this chapter can feel a little tricky, right? But don't you worry, my promise is to make it so simple, so clear that you'll be completely ready for your exams. Chalo, let's start.
So to get started, let's talk about something we literally use every single day. What's the magic behind our Wi-Fi? Just think about it for a second. How does your Wi-Fi work without any wires? Or your mobile signal? Forget that. What about sunlight? It travels millions and millions of kilometers through totally empty space to reach us. How is that even possible? Well, the answer to all these questions is the same. It's the magic of electromagnetic waves. And that's exactly what we are going to master today. Okay, so to understand this magic, we need to look at this amazing partnership. It's almost like a dance, A dance between two partners, the electric field, which we'll just call E, and the magnetic field, or B. Let's imagine this. Picture a super crowded room, okay? Jam-packed. Now, if one person gives a little push, what happens? The person next to them will sway, right? And that sway will make the next person push someone else. And this push, sway pattern will travel all the way across the room. See? The disturbance travels, but the people themselves don't move across the room. This is exactly what's happening here. The changing electric field is like that initial push, and that push creates a sway, which is our magnetic field. Then that sway creates another push, and this is how they create each other, sending a wave through completely empty space. So what's the most crucial point here? It's this two-way street. It's a deal they have. A changing electric field, E, creates a magnetic field, B, and a changing magnetic field, B, creates an electric field, E. They just keep making each other, again and again. But Cho, please remember this. If you get this one idea, you've understood the heart of this entire chapter. Seriously. Okay, so the crowded room story is great for our understanding, right? But for the exam, for full marks, what do we write? For that, we have to look at the proper exact NCERT definition. Here it is. This is the golden line from your textbook. It says, time-dependent electric and magnetic fields give rise to each other. Now, don't get scared by the term time-dependent. It's just a fancy, exam-friendly way of saying changing. That's it. So a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. See? It's the exact same EB dance we just talked about, just in official language. Now, you'll often hear this word self-sustaining. What does that even mean? It's actually really simple. Think of it like a relay race or a chain reaction. E creates B. That B then creates a new E. That new E creates a new B, and it just goes on and on and on. The amazing part is, once this wave starts, it doesn't need its original source anymore. It's like, okay, thanks for starting me. I can take it from here. It just travels through space all by itself. So this is what it actually looks like. You absolutely have to know this for your exam, so pay close attention. You see the electric field, E, waving up and down on one axis. Then you have the magnetic field, B, waving side to side on another axis. And where is the wave actually going? It's moving forward, along the third axis. The key thing to see here is that all three of them, the E field, the B field, and the direction the wave is traveling, are all at 90 degrees to each other. They are mutually perpendicular. Super important point. Okay, so let's quickly put all the pieces together. How is an EM wave actually born? Let's go step by step. First, you need a source. What's the source? It's a charge that is either accelerating or just, well, jiggling back and forth. This jiggling charge creates a changing electric field around it. Okay, step 2. We know what a changing E field does, right? Yep, it creates a changing magnetic field. Step 3. Now what does this new changing B field do? Of course, it creates a brand new E field. And the cycle just keeps repeating itself. This self-sustaining disturbance then travels out, away from the charge, at the speed of light.
Chalo, enough theory for now. Let's solve a very, very simple numerical problem. Trust me, these are easy marks in your exam, so let's make sure we get them.
Okay, so here's the question. A radio station broadcasts at a frequency of 100 megahertz. Simple. We need to find its wavelength, which we call lambda. Now, there's one simple formula that connects everything. You've probably seen it before. Speed is equal to frequency times wavelength. So if we just rearrange that a little bit, we get wavelength, lambda, is simply the speed divided by the frequency. And for an electromagnetic wave, what's the speed? It's always the speed of light, c. So let's just plug in the numbers. Wavelength is c, which is 3 × 10⁸, divided by the frequency. Now, 100 megahertz is 100 into 10 to the power of 6, which is just 10 to the power of 8. So you have 10 to the power of 8 on top and 10 to the power of 8 on the bottom. They just cancel out. And what are we left with? Just 3. 3 meters. That's it. It's that simple. And a fun fact, this is actually why old radio antennas used to be so long, often a few meters in size. All right, now for a very important section. Let's talk about some common traps. I call them silent killers because they quietly steal your marks in the exam. Let's make sure you don't fall into these traps. Okay, mistake number 1, and this is a big one. Many students think that EM waves need a medium to travel, like how sound needs air. Absolutely wrong. In fact, it's the total opposite. EM waves travel the fastest and are the happiest in a complete vacuum, in empty space. And the reason is simple. They don't need anything to travel in because the changing fields are the wave itself. They are their own medium. And the second common mistake is thinking of the electric and magnetic fields as two separate things that just happen to be together. No, no, no. They are inseparable. They are two sides of the same coin. You can't have one without the other. A changing E field always creates a B field, and a changing B field always creates an E field. It's not two separate things. It's one single beautiful phenomenon called electromagnetism. So you may be thinking, okay, this is interesting, but why is this chapter so important? Well, because this is like the grand finale. This is where everything you've learned about electricity and magnetism so far finally comes together. It connects all the dots. Just think about it. You've already studied Faraday's law, right? What did it say? That a changing magnetic field creates an electric field. Then you learned the Ampere-Maxwell law, which says that a changing electric field creates a magnetic field. Well, this chapter is where those two big ideas meet. When you put them together, what do you get? You get the perfect description of light itself. It's this beautiful moment where electricity, magnetism, and light all get unified into one single idea. Amazing, isn't it? Tika, so before we wrap this up, let's do a super quick revision. These are the absolute key points you must have on your fingertips for the exam. Okay, let's go. Point 1, what is the source of an EM wave? An accelerating charge. Got it. Point 2, how are the fields arranged? E, B, and the direction of travel are always perpendicular to each other. Point 3, how fast do they go? In a vacuum, all EM waves, from radio to X-rays, travel at the same speed, c. Point 4, where does this speed c come from? It's a fundamental constant of the universe related to mu0 and epsilon 0. And finally, point 5, the relationship between the fields is super simple. E equals c times b. That's it. If you remember these 5 points, you are in great shape. And I'll leave you with one final interesting question to think about. We know these waves carry energy, right? That's how the sun warms us. But they also carry momentum. So, if light is an EM wave and it has momentum, does that mean light can actually push things? Can a beam of light exert a force? Think about that. We'll explore that later. Fantastic work today, Butcho. Well done.